Today is part 2 talking about variation of parameters, and today we're going to talk about using variation of parameters to find general solutions to non-homogeneous Cauchy-Euler ODEs. As we noted yesterday, the method of undetermined coefficients can only be used to guess a particular solution to a differential equation with constant coefficients, which meant it was completely off the table for a Cauchy-Euler equation. But variation of parameters is what allows us to solve a non-homogeneous Cauchy-Euler equation, and that's what we're going to do today. Let me demonstrate it by example. So the first one we have is x squared y double prime minus x times y prime plus y is equal to 2x. This is a Cauchy-Euler equation because if I look on the left-hand side, the number of x's is always an exact match to the order of the derivative of y. 2x's, y double prime. 1x, y single prime. No x's, y with no primes. So having acknowledged that, let's start as always by finding y sub c. Let's find the solutions to the version of this equation with 0 on the right side. Now, for a Cauchy-Euler equation, our guess is different than what it is when we have a constant coefficients equation. For a Cauchy-Euler, we guess y equals x to some power called m, which implies that y prime is equal to mx to the m minus 1, and y double prime brings down m and an m minus 1. So if I put that information into my differential equation and simplify, I get m times m minus 1 times x to the m minus m times x to the m plus x to the m is equal to 0. And if I continue to simplify, dividing out the x to the m's, I get m times m minus 1 minus m plus 1 equals 0, which can be rewritten as m squared minus 2m plus 1 equals 0. So this splits as m minus 1, m minus 1. So we have a repeated real root, and that means that our independent solutions are given by y1 equals x and y2 equals x times natural log of x. With this, we can get our complementary function c1 times x plus c2 times x times the natural log. Next, we need to go ahead and find one particular solution. Now, if I scroll back up to my non-homogeneous ODE, before I extract the value of f of x, I need to note that currently the differential equation is not in the right format. In order to get it in the right format, I need to start by dividing everything by that x squared who is currently with our y double prime. So we get y double prime minus 1 over x y prime plus 1 over x squared times y equals 2 over x. And this 2 over x is the actual value of f of x that we need for the variation of parameters formula. So let me make a note of that down below. We're also going to need to figure out the value of the Wronskian. So let's calculate W. In our first row, we have our two complementary solutions. And in the second row, we have their derivatives. So 1 is the derivative of x, and the derivative of x times natural log of x simplifies to 1 plus natural log of x via the product rule. So if we calculate that determinant, we get x plus x times natural log minus x times natural log, and therefore the Wronskian simplifies just to x. Now we have everything that we need to assemble our formulas for u1 prime and u2 prime. u1 prime was equal to negative y2 times f of x divided by x. Now y2, let's recall, was equal to x times natural log of x. We found that our function f of x, after rewriting our differential equation in the correct format, was equal to 2 over x. And we also have the x coming from the Wronskian in the denominator. So u1 prime simplifies, looks like negative 2 natural log of x over x. Oh, this is blessed. You can tell I didn't write this problem myself, because if I integrate this, then via chain rule, we get negative natural log squared of x. Let's repeat the calculation for u sub 2. U sub 2 prime is equal to our first complementary solution. Our first complementary solution being just x, multiplied by our function f of x, and divided by the Wronskian that we calculated. And therefore u2 is equal to 2 times the natural log absolute value of x. Now you can leave it as absolute value of x, or you can change this to just regular old x. It was a long time ago, but you may remember that for Cauchy-Euler, we always assume that x is strictly positive. So that's one way to simplify this expression a little bit. You don't need to take the absolute value of x if x is already strictly positive. So with that, we can assemble our particular solution. Our particular solution has the form u1, which is natural log squared, negative, multiplied by y1, which was equal to x, so I'll squeeze it in the front. And then u2 prime, and then u2, which was 2 natural log x, multiplied by y2, which was x times natural log of x. So this yp can actually be simplified. This can be turned into simply x times natural log squared. And therefore our general solution is the sum complementary solution plus single particular solution. Let's demonstrate the method in another example. In this case, we have x times y double prime minus 4 times y prime is equal to x to the 4th power. So step number 1, we need to find the complementary solution using the same techniques as always. Now, as of this moment, this may not quite seem like it's in the format of a true Cauchy-Euler equation, because the number of x's is not a consistent match to the order of the derivative on the y. But we can remedy this by multiplying everything here by x. If I multiply through by x, then the x times y double prime will become an x squared times y double prime. And the negative 4y prime will become a negative 4xy prime. If you multiply 0 by x, then that's unchanged. So now this has the form of a true Cauchy-Euler equation. And we can make the appropriate guess that y is equal to a solution of the form x to the power m. From this, we get our usual auxiliary equation, m times m minus 1, x to the m, minus 4m x to the m. There's no term with just y, so then we would just get 0. Or m squared minus 5m equals 0. So from that we get two solutions corresponding to m equals 0 and m equals, positive 5. So y1 is just the constant, is just x to the 0, which is the constant number 1, and y2 is equal to x to the power 5. That gets us a complementary solution of the form c1 times 1 plus c2 times x to the 5th power. Step 2, let's find our particular solution. And again, since we have a differential equation which does not have constant coefficients, variation of parameters is our only choice. So going back up to our original ODE, currently y double prime does not stand alone. So in order to see our true value of f of x, we're going to need to divide out the x that is currently in the way. Once we divide everything by x, we can see our true value of f of x. Our true value of f of x is the x cubed on the far right side. We're also going to need to get our Wronskian. So I'm going to fill the Wronskian up with our two independent complementary solutions and with their derivatives. So this simplifies to 5x to the 4th power. The anti-diagonal is just 0, so it won't affect anything. Okay, so now let's set up our equations for u1 prime and u2 prime. u1 prime is equal to negative y2 multiplied by f of x, who was x cubed, divided by the Wronskian. So after simplification, this looks like x to the 4th power times negative 1/5. So integrating that is really easy. It's just a power function. The integral is u1 equals negative 1 over 25 x to the 5th power. u2 prime, meanwhile, would be equal to positive y1, so positive 1, multiplied by x to the 3rd power, divided by our Wronskian. So this simplifies to 1 over 5 times 1 over x. And the integral of that is u2 equals 1/5 natural log of x. And just as in the previous example, I'm just ignoring the absolute value because we're assuming that x is strictly positive when we work with Cauchy-Euler equations. So our particular solution, if we assemble it according to the variation of parameters formula, is u1. u1 was negative 25 x to the 5th power. multiplied by y1, which was just equal to 1, and u2 multiplied by y2. Now that we have our complementary solutions and our particular solution, of course we can assemble into our general solution. The general solution is the complementary solution plus our particular solution. Now you can once again simplify this a little bit by combining these two terms in the middle here, but there's not really any need to do that, so I'm just going to omit it. Let's go ahead and try an initial value problem. An initial value problem is only one step different from what we've done before. We're going to have to find the general solution first, and then in a final step, we'll have to figure out the values of C1 and C2, which are necessary to satisfy the initial condition. So, it begins exactly the same way that it began before. First, let's find the complementary function. Now again, this may not seem like a true Cauchy-Euler equation, but this is equivalent to x squared y double prime plus xy prime is equal to 0, and you can find that by multiplying everything by an extra copy of x. So we're going to make our usual guess for a Cauchy-Euler equation, x to the power m, and that will lead to the auxiliary equation m minus 1 x to the m plus m x to the m is equal to 0, which simplifies to m squared minus m plus m equals 0. So m equals 0 is a repeated root. And that gives us two solutions. y1 is equal to x to the 0 power, which is just 1, and y2 is equal to x to the 0 power multiplied by the natural log of x, which is the same thing as simply natural log of x. So now we have our complementary solution. Our complementary function is c1 times 1 plus c2 times natural log. Next, let's use variation of parameters to find one particular solution. So scrolling back up to my differential equation, let's start by identifying the true value of f of x, which requires us to rewrite the differential equation in such a format that y double prime stands alone. So in this case, dividing everything by x to isolate y double prime, we see that the true value of the function on the far right side is 1. Let's also get our Wronskian. So our two complementary solutions were 1 and natural log of x. The derivatives are 0 and 1 over x, and therefore the Wronskian is equal to 1 over x. The formula for y1 prime would therefore be negative y2 multiplied by f of x divided by the Wronskian, which simplifies to negative x natural log of x. Now to integrate this, one would need to do integration by parts, which I think is going to give us negative x squared over 2 natural log of x minus the integral of negative x squared over 2 times 1 over x, which simplifies, it looks like negative x squared over 2 times the natural log of x plus x squared over 4. Similarly, for u2 prime, y1, which is 1, multiplied by f of x, which was also 1, divided by the Wronskian, which was 1 over x. So that simplifies to just x, whose integral is given by x squared over 2. From this, we can assemble our particular solution. The u1 that we found, negative x squared half natural log plus x squared over 4. Multiplied by our first complementary solution, just 1. And then our u2, x squared over 2, multiplied by our second complementary solution, which was the natural log. Now we can actually clean this up. We have a negative x squared half natural log. We have a positive x squared half natural log. So y sub p can be reduced to this term, x squared over 4. And from that, in step number 3, we can assemble the general solution. Take our complementary solution from step number 1, and then add the particular solution from step number 2. So the last thing that we need to do, the final step for this particular question, is to figure out the values of C1 and C2 that would be needed to satisfy the initial conditions. So we need y1 to equal 1 and y prime of 1 to equal negative 1/2. So to that end, let's calculate y prime so that we know what we're plugging 1 into. C1 will vanish, natural log will become 1 over x, and x squared over 4 will become x over 2. If I plug 1 into the original function, then I get C1, natural log of 1 vanishes, plus 1/4. And if I plug 1 into the derivative, then I get C2 plus 1/2. Ooh, look how easy this system is to solve. That gives us immediately that C1 equals 3/4 and C2 equals negative 1. And therefore the solution to this initial value problem is equal to 3/4 minus 1 times the natural log of x plus the particular solution x squared over 4. That concludes today's material. We practiced using the variation of parameters formula to find particular solutions to Cauchy-Euler ODEs. Now we know how to completely solve any non-homogeneous Cauchy-Euler ODE or any initial value problem containing one of those.